good morning or good afternoon, depending on where you're joining us from, everyone. My name is Jesse, and I am with Exploring by the Seat of Your Pants. If you're joining us for the first time today, we are all about bringing conservation, adventure, and science into classrooms around the world. And I want to do a special shout out to all our teachers joining us live and on YouTube today, because this has been a crazy month. I think by the end of the month, I see this almost every month. I swear we get bigger every single month, but I think this is our all-time record for most programs in one calendar month. I think 65 or 70 this month, which is crazy. So thank you so much for continuing to support us as we showcase such amazing scientists, explorers, and places from around the globe. Now, October is classically Space Month, and as befits that theme, we've had on astronauts, engineers, all sorts of amazing people in NASA, Europe, all across Canada, and more. But today, as we near the end of our month, we are bringing back in one of my very favorite speakers, Nathalie Ouellette. So she is the outreach scientist for the James Webb Space Telescope. She's going to be telling us a lot about that today. She hunts exoplanets out of Montreal. She does all sorts of amazing stuff as an astrophysicist, and I'm so excited to dive in with the broadcast with her in just a second. Although, as a quick housekeeping note, we have a little bit of fewer events this week, and that means that we are able to create a Kahoot quiz. So if you guys want to test your understanding, have a little fun at the end of the broadcast, Kahoot.it for all of you with the game pin 4894640. I will bring that up again at the end, but if you'd like to participate at home or in your classroom, feel free to click that as a separate tab. Now, without further ado, I'm going to turn over to Nathalie to blow your minds. Thank you so much for joining us again, Nathalie, and take us away.
Thank you so much, Jesse. It's always such a pleasure to be here. And thank you for joining from all over the world. I hear that there's people on the West Coast, and I'm here on the East Coast. It's starting to feel a lot like fall here. I hope the weather is nice where you are. So I'm Nathalie Ouellette. I am an astronomer or astrophysicist. Pretty much the same thing. We don't mind which one you call us. And I'll be talking about lots of different things that I do, including the James Webb Space Telescope. So it's my pleasure to be with you today and talking about that. So as I mentioned, I'm an astronomer or an astrophysicist. And when you think of that, maybe the first tool that you think that we might use is a telescope. So you might have a telescope in your classroom or at home, and you're imagining something, a long tube on a tripod, and you take it out at night to observe the stars and planets, and it's great fun. I had one growing up as a kid, but when you become a professional astronomer, you got to step up your game a little bit. It has to be like a bigger telescope that can look at things that are fainter in the sky and farther away. So these are two examples of telescopes that I've gotten the chance to visit and use before in the past. And they are located in Hawaii on a mountain called Mauna Kea. So when you think of Hawaii, you probably think of a tropical beach with palm trees and like nice warm weather. You might not be thinking of a really tall mountain with snow in front of a really big telescope here. So you can see the snow actually here. But this is one of the tallest mountains in the world and one of the best places to do astronomy in the world. So these telescopes cost hundreds of millions of dollars. So you really want to put them in the best spot. You don't want to put them in the center of a city where it's raining and there's light pollution. You want to put them far away from cities where you don't have a lot of light pollution, so you can have a beautiful dark night sky. You want to put it high up. That way you're above a lot of the clouds. You have drier air, so you don't have a lot of fog or mist or clouds that are bothering you. And also, you want the air to be thinner. So on these mountaintops, there's less oxygen, less air. Not so good for breathing, but that's why you don't stay there for nights and nights at a time. You only stay there one night, then you come back down. But because there's less air, the air is stiller. That means that you don't get twinkling of stars. You get nice, crisp, clear, not blurred images. So this is why you want to have these telescopes high up on these mountains or these desert plateaus. And Hawaii is one of the best places to do that. So the telescope, you can see the foreground that I'm circling right there. That's called the Gemini telescope. Gemini, you might recognize, is a constellation or a zodiac sign. It's the twins. So if this is Gemini, it needs to have a twin, right? So there is a twin telescope that looks exactly like it in the southern hemisphere in a place called Chile. So that means that you can have the north one in Hawaii that looks up at the northern sky and one in the south that looks down at the southern sky. So you can see the entire sky that way. It's a big mirror, 8.2 meters wide, and lots of people use it. Canadians use it, Americans use it, English people use it, British people use it, lots of people from all around the world. The one at the back is called the Canada, France, Hawaii telescope, a smaller mirror, 3.4 meters wide, and people from Canada, France, and the University of Hawaii use it. So these are some of the telescopes that we get to use as Canadians and other people get to use all over the world as well. Another telescope I've had the chance and the privilege to use is called the Sloan Digital Sky Survey, or SDSS telescope. And you can see it looks a little bit different. It's not inside of a dome. It is housed in sort of like a garage kind of thing, and you can roll back the roof of the garage at night to do your observations. It has a round mirror despite being housed in sort of like a square or rectangular box. And the main difference with this telescope, the other telescope that I mentioned, in order to use data from that telescope or point the telescope at your favorite object to do your science, you need to be a member of the country or the university that owns the telescope. They're called private telescopes, or public if they belong to a country, but it has to be someone who was from that country that uses it. The Sloan Digital Sky Survey takes pictures of the entire sky many, many times at a regular basis and takes all of that data and puts it available for anyone in the entire world online. That has opened up astronomy a great amount. So you have people in developing nations in Africa, in Asia, in Oceania who might not have access to a telescope like Gemini or the CFHT, but they still really love space. They want to do science, so they get to have access to data from the Sloan Digital Sky Survey, for example. Even you at home right now or in your classroom after my presentation, you could go on sdss.org and look at that data and do your own science and space projects if you wanted to. So the telescopes I've mentioned up until now are ground-based. They are located on the Earth. But I mentioned, where do you want to put a telescope? You want to put it away from city lights. You want to put it high up where the air is thin and still and you're above the clouds. And there's no better place that matches those conditions than space. So we put some telescopes up in space, but there are some disadvantages as well. If you're putting it up in space, you need to find a rocket. You need to get a lot of fuel, and it's very expensive to put it up. And once it's up there, it is harder or even impossible to fix or put new instruments on it over time. So you have to have both types of telescopes, some that are on the ground on Earth, some that are in space, and they often work together. So these are two famous space telescopes. One is already up there in space. It's called the Hubble Space Telescope, and I'm going to talk a little bit more about some of the great things that it's done, but it's been up there for a little while now, 31 years. So we've had to think of its successor, not its replacement, because we're hoping both telescopes will be friends and work together for a good number of years, but its successor, and that's the James Webb Space Telescope that you can see here. It was in a lab when this image was taken. It is now, very recently, it has arrived in South America and will soon be launched into space at the end of this year. So I'm very, very privileged to be part of that mission, and I'll talk about that mission a little bit more. On top of being part of that mission, I also work at a place called the Institute for Research on Exoplanets at the University of Montreal in Canada. So we are about 60 people, astronomers, from students to professors, and we are using telescopes like the ones that I've mentioned to search for new worlds and search for extraterrestrial life, alien life. So I'll talk a little bit about that, and you can ask me all the questions you want about aliens, whether I believe them or not, believe in them or not. But this is what we're looking for. So it's not just in the realm of science fiction anymore. We're really looking for alien life at places like this institute. So to talk about these new worlds that we're searching, we can start in our own solar neighborhood. So our solar system consists of the sun, which is a star, and planets orbiting this star. So we have 8 planets in our solar system. We have dwarf planets, which include Pluto. We have comets and asteroids as well. So the planets that we have 4 rocky or terrestrial planets that are close to the sun: Mercury, Venus, Earth, and Mars. And we have 4 giant gas planets that are farther away from the sun: Jupiter, Saturn, Uranus, and Neptune. And beyond that, we have dwarf planets such as Pluto and other planets as well, other dwarf planets as well. But in our solar system, everything is centered around the sun, which is simply a star, like many other stars in the night sky. So for centuries now, scientists and astronomers have looked up at the night sky and thought to themselves, if our star, the sun, has planets, why couldn't all of these other stars also have planets? So this concept of other worlds beyond our solar system has existed for many centuries, but it's very hard to observe or look at these planets because their star that they're orbiting is so bright that they get lost in the glare of their star. So we haven't had the technological tools or know-how to observe them for the longest time, but the idea's been there for a while. So this idea is what we call an exoplanet. It's simply a planet that orbits a star other than our sun. So exo comes from the ancient Greek, which means outside. So it's just a planet outside or beyond our solar system. So we've had this in our minds as a humanity, as a civilization for hundreds of years, but it wasn't until 1995 that we were able to detect the very first exoplanet around a star that looked a lot like our sun, actually. So the name of this planet is 51 Pegasi b. It's a bit of an odd name, and if you're interested in why it's named like that, you can ask me afterwards. But it was discovered in 1995. So I think most of you out there, 1995, that sounds like a long time ago. That happened way before you were born. But 1995 was only 26 years ago. This discovery is actually younger than I am. It's actually much younger than most people who study exoplanets now. So we often call astronomy the oldest science in the world. We've been doing it for millennia, for thousands of years. And humans have been looking at the stars for that long. But to live in a time where we can now, for the first time, observe these exoplanets and this whole new field of astronomy is being born is quite exceptional. We are living in a really special time in the history of astronomy. So this planet being discovered was a huge discovery because, of course, it was the first exoplanet. But there was another reason why this discovery was very significant, and it's because of the type of planet that it is. So I mentioned in our solar system, we have the four rocky planets that are close to the sun, the four gas giant planets that are farther away from the sun. This is sort of like a mix of both. This is the type of planet called a hot Jupiter. This is a planet that is almost the size of Jupiter. It's about half the size or the mass of Jupiter, but it's very close to its star. So looking at this diagram here, we can see our sun and the orbits of the rocky planets in our solar system, Mercury, Venus, Earth, and Mars. So Mercury is the closest one. If we're looking instead at the diagram of the orbit of the exoplanet, 51 Pegasi b, we can see that it is much closer to its star than even Mercury is to the sun. It's 20 times closer. That means that it's a Jupiter type planet, but it's very, very hot because it's so close to its star. That's why we call it a hot Jupiter. And before we made this discovery, we didn't think this type of planet could even exist. We don't have a type of planet like that inside of our solar system because we thought that the energy and the heat from the star would blast off, just evaporate all of the clouds on this type of planet. So when we discovered it, we were like, wow, the first exoplanet, super exciting, but also this opens up a whole new type of planet that we didn't think was possible. And since then, we've discovered lots of other types of planets that don't exist in our solar system, but exist outside of our solar system. Since that first discovery in 1995, we've discovered thousands more exoplanets, over 4,400 to this date, and every day we discover new exoplanets. Now, all of these images of exoplanets you can see here are drawings or artistic representations. So I mentioned it's very hard to observe an exoplanet. We can detect them now, but for the most part, we can't take nice pictures of them the way that we can take pictures of the planets in our solar system, just because they're so far away and they get lost in the glare of their star. But we can still study them, observe them, and determine things like their size, their colors, their temperatures, if they have rings or not, if they have moons or not. So we can imagine what they might look like. And we think it would look something like this. So one of the tools that's coming up is really going to help us study these exoplanets is the James Webb Space Telescope, especially because of the instrument that Canada contributed to the mission. So this is a mission, the Webb Telescope, led by NASA, which everyone knows and loves, and they also led the Hubble mission. The European Space Agency is also involved, and they were involved in Hubble as well. But the Canadian Space Agency is involved in Webb, which is really exciting because we weren't formally involved in Hubble. This means that we contributed something to the mission, and Canadian astronomers will have privileged access, special access to data and time on the telescope. So, very, very exciting. So I am really, really happy to be part of this mission. I'm what we call the outreach scientist in Canada. So I'm an astronomer, like I mentioned, and I'm part of the scientific team. But my goal in the mission is to act like a bridge between the science team and the general public. So that means when there are huge discoveries that happen with the telescope or exciting news related to the telescope, it's my job to write a text or film a video or do a presentation or give an interview on TV or on the radio that explains that accurately, scientifically accurately, but in a way that people can understand. Because sometimes scientists, they're so involved in their work, it's sometimes hard for them to speak the same kind of language that the general public understands. So it's my job to make sure that that message passes properly between the two sides of that equation. And I got to visit the telescope a few years ago when it was being tested on in California, but it's no longer there. It just arrived on its launching pad in South America a few weeks ago, and it's being prepared right now to be put inside of a rocket to be launched into space December 18th. Now, I mentioned the Hubble Space Telescope a little bit before. Here it is, a closer view. And it's been up there for 31 years, like I mentioned. At the very start of the mission, there were actually a few issues with its mirror, but luckily, it's only about 550 kilometers above our heads in orbit around the Earth. So we were able to send an astronaut there using the Canadarm actually to fix the mirror. And now it works beautifully. It's been taking incredible images of the sky and been doing really amazing discoveries related to space. So it's over 31 years old. It's still functioning, but the technology that it holds is starting to be a little bit past its expiration date, let's say. So we wanted to think of the next generation of telescope, and that is the Webb telescope. So to give you a little bit of a comparison between the two, you can see that Hubble has that sort of tube shape. The mirror is inside. It's a 2.4-meter wide mirror, so it's quite large. But we wanted something bigger for Webb. We wanted something 6.5 meters wide. You can also see that Webb has its mirror outside of a tube. There's no tube here, and that's because of the type of light that each telescope looks at. So you can think of Hubble like a giant human eyeball that looks at the same kind of light that the human eye can. So the visible light, all the colors of the rainbow, everything that you can see around, that's basically the type of light that Hubble looks at. Webb instead looks at a type of light called infrared light, which is invisible for the human eye. But there are lots of things in space, in the universe, that shine very brightly in the infrared. So it's important to look at that type of light too. Infrared, you might think of when you're looking at a science fiction movie or an action movie, and people put on night vision goggles to look at other humans or animals in the forest at night. Infrared light is very associated to heat, human temperatures. And so we don't want to trap heat with the telescope inside of a tube, which is why the mirror is out in the open. And you can also notice that there's like this big sun shield. I'll explain a little bit what that's for in a moment. So you saw in the comparison between the two, Webb is much, much bigger than the Hubble Space Telescope. And one of the challenges of that is to try to fit it inside of the rocket that's going to launch it into space. So in order to do that, the telescope had to be developed in order for it to fold on itself like a piece of origami. So once it's launched, it will actually need to unfold itself. So you can see the bottom of this animation, you can see the movement of the telescope as it's being launched from the Earth. It will pass the moon and end up at its final destination, 1.5 million kilometers from Earth. That's 4 times the distance between the Earth and the moon. So if something breaks, we can't fix it like we did for Hubble. And on its journey of 30 days to go to its final destination, it will need to unfold because it was all sort of packed up and folded on itself inside of the rocket. So it will need to deploy its solar panels, which gives it energy. It's going to need to deploy its antenna so that it can communicate back with Earth. And it's going to need to deploy its giant sun shield that I mentioned. So I mentioned the link between infrared light and heat. Now, infrared light comes from other places in space like the Earth or the moon or the sun, but we don't want to study those objects with this telescope. We need to instead block the light from the sun to protect the telescope. So it needs to deploy a giant sun shield about the size of a tennis court. It's 5 layers of reflective material. It's the equivalent of a sunscreen with an SPF of 1 million. So it blocks out a huge amount of the sunlight. So you can see it being deployed here very carefully because we don't want it to tear. It's pretty delicate. And it will always be oriented such that the sun shield will be between the sun and the mirror and its instrument. So we keep the instrument and the mirror cold. And then finally, it needs to deploy its telescope, its mirror parts, so that it can actually look out into space. So this is very, very delicate. About 300 different little mechanisms need to be activated in order for this telescope to fully deploy, get to its final destination, and be able to work. So it's a very delicate mission. On top of being a huge revolution scientifically, it is a huge challenge, technologically speaking, and it required about 10,000 scientists working together all over the world to make this happen. So I mentioned infrared astronomy. Now, why infrared astronomy? Why is it important? So you can see here different types of light in the electromagnetic spectrum. Visible light is this part here, the colors of the rainbow that we can see. This is what Hubble looks at. If you look at light that is more red than red, you get infrared light here. This is the part that's interesting to the Webb telescope, and that's because lots of things in space shine in infrared light. One example is planets. This is a picture of the planet Jupiter taken in an infrared light. You can see it's glowing very brightly. It's the North Pole of Jupiter. Solar systems and stars being formed are very bright in the infrared light as well. And certain types of galaxies that are very far from us have also light that stretches to the infrared. So if you want to study galaxies, we need to study infrared light. Another reason why infrared light is really useful is because space is a really dusty place. Dust is being blown off by a bunch of stars all around us, and this dust blocks out visible light. So this is a picture of a nebula called the Pillars of Creation in the Eagle Nebula. And all of these darker areas are actually dust lanes that are blocking out visible light. But if you're looking at exactly the same part of the sky in infrared light instead, you see that all these other things are being revealed behind this veil of cosmic dust if you look at a different kind of light. So by looking at infrared light, we can actually open up this brand new window to the universe using the Webb telescope. So the Canadian instrument, this is what our contribution is here, and it's a double instrument. It's about the size of a washing machine. It has a guiding camera called FGS, which will allow the telescope to point and stare at any object and take really, really nice images so that the telescope isn't sort of like vibrating and making blurry images. And the other piece is a scientific instrument called NIRIS. It's a combination of a camera and what we call a spectrograph, which is sort of like taking rainbow pictures of different types of light and different objects out there. And it'll be able, in part, to study exoplanets and find out if there are clues of life inside of these exoplanets. So there are different scientific missions for Webb. Alien worlds is something that interests us enormously. I mentioned exoplanets, but also looking at the worlds in our own solar system to figure out if they could have signs of life. How stars evolve over time from when they are born to when they die, and sometimes when stars die, they become black holes. This is another big scientific goal of James Webb. Studying galaxies through time, we want to try and look at galaxies at different stages of their evolution, from when they were born to how they look like now, and pushing the boundary and trying to look as deep into the universe, as early in the universe as possible, almost right after the Big Bang, only 200 million years after the Big Bang. And so we want to really try to look at the very, very early universe using this. So these are the different scientific missions for James Webb. We're very excited about it. I hope that you'll stay tuned. December 18th is our planned target launch date. It might move a little bit, but we are ready to launch it. And then afterwards, we're going to be doing some testing. But starting next year, we're going to be starting the scientific operations of James Webb. So stay tuned. There's going to be some amazing discoveries that are going to happen very, very soon. And I hope that I've convinced you that it's going to be a huge revolution and that you will stay on the lookout for all of these pieces of discovery coming up. Thank you.
Thank you, Natalie. What a fun presentation, as always. That was great. I'm going to dive in with a question of my own because you highlighted it in your broadcast, but I do want to feature for everyone who's tuning in live and on YouTube, if you guys want to play along with a little quiz after this first question before we dive into the Q&A, Kahoot.it. You can play this with your class if you'd like. If you have your individual devices, great. And if you'd like to just play along and talk with your class, you're welcome to do that. But while everyone's signing up to that, Natalie, you talked about aliens. So you said the main question you get, do you believe in aliens? Are they out there? What's going on? Tell us.
Yeah, so there's like two parts of that question that I can answer. So I talked about all these exoplanets that we discovered, and that's really just the tip, the like mini tip of the iceberg. We think that inside of our galaxy alone, there's probably hundreds of billions of exoplanets out there. So it's my opinion that if Earth is the only place that life was able to develop, it's a big waste of space. It's pretty improbable that we are the only place where the conditions are right for any kind of life to evolve. That being said, life can include very simple forms like microbes or bacteria. For the longest time on Earth, for billions of years, the type of life we had here was very simple. It wasn't humans, it wasn't even dinosaurs or, birds and lizards walking around. It was simple. So I do believe that there is alien life, be it simple forms of life, out there. That being said, I do not believe that they have been able to come here and contact us or visit us because the distances to travel, even for just information in terms of radio communications travel, are so vast. So I think they exist, but I don't think they've visited us.
I love the nuance, and thank you so much for that great answer. I love the idea of it as a waste of space. I know a lot of our kids won't have seen the Contact movie, but it's one of the great sci-fi movies of all time, and that's the argument that they largely make in it, which is just awesome. Guys, let's dive in with Kahoot. A bunch of you have already gotten on board. So, Natalie, this is your first Kahoot quiz with us too, and maybe when there's like 5 seconds to go for each answer, you can help us out if people are having any trouble. But I'm going to start with our folks so far. If anyone wants to join in after we've gotten underway, you are welcome to do so. But let's dive in with our first question with this spooky background as we get close to Halloween. All right. 3, 2, and 1. You don't win any prizes, but you do win our everlasting respect if you come first. How many planets have we discovered outside of our solar system? 1, 10, hundreds, or thousands? We've got 7 answers so far, 15 more seconds. Way to go, guys. Keep coming in with those answers. Maybe some of them look like this fancy thing with like the cool aurora thing and the double moon. We don't know. We're going to, that's what advanced telescopes and great exploration are for. So most of you guys got that right. What are we at? Like, what's the specific, do we have a specific number for this, Natalie, yet?
Like 4,500 is the current tally.
Fantastic. All right. Who's on our lead? Clever Urchin, 936. Way to go. The faster you answer, the more points you get. Question number 2. What's the name of this current best telescope / Stanley Cup in space? I never thought of it this way before until this picture.
It does look like the Stanley Cup. It does.
I think that's our Canadian plug of the day. So here we go. James Webb Space Telescope, Planet Seeker 9000, Apollo, or Hubble. What is this thing? We highlighted it so much today. I think they should know. We're going to find out. 25 answers. Most of you got that right. A few of you were tricked by the fact that we're mainly talking about James Webb today. That's okay. Captain Lark takes the lead. Barely, though. Clever Urchin, you're right there. You're right there. Now, I like this. I don't know if we talked about this too much today, but it's just one of my favorite ideas. When you look through a telescope, you're looking back through time. True or false? You have like 4 seconds, people. 4 seconds. And the answer is, ooh, we were mixed and we're not sure.
Ooh.
Natalie, tell us about this. I'm like, this is my favorite thing in science. It's just so cool.
Yeah. So looking through a telescope is like looking through a time machine because we can only study objects using the light that they send out. But light doesn't move from point A to point B instantaneously. It takes a little bit of time. It's the fastest thing that is in the entire universe, but the distances are so vast. And that's actually why we used light years as a kind of measure of distance. It's the distance that light can travel in a single year. So if you're looking at a galaxy that's 1,000,000 light years away, that means it took 1,000,000 years for that light to go from the galaxy to us. So the light that we're looking at is 1,000,000 years old, and we're actually looking at the galaxy not as it exists now, but as it existed 1,000,000 years ago. And then you can think of something that's like 1,000,000,000 light years away.
Crazy.
You're looking at it 1,000,000,000 years ago.
I love it. So I mean, if you're looking at something 1,000,000 light years away, it could have exploded.
It could have. It's
800,000
true.
years ago, and we have no idea. And we won't know for like 700,000 more years. It's crazy. I love it. Let's do our final question. Where are we at in our leaderboard? Silver glider coming in. Our final question. James Webb Space Telescope was coded in what material? I don't know. Maybe the Frodo here playing with something might give an indication. We're gonna find out. I don't think there's any cool writing on.
You can look at my necklace too.
You can. Yeah. Okay. 6 more seconds. I think everyone's got in their answer. Way to go, everybody. 2, 1, silver, bronze, gold, platinum, gold. Wow, but a nice mix. Gold is our answer. So that is our final tally. Let's see you on the podium, and then we're going to dive in with questions for all our live classes. Okay. By the way, if you're on the podium and you want to identify yourselves in the classes or on YouTube, please do let me know where you are. I'm using Gator number 2. Who did we get? Our winner. It wasn't me, I promise. I didn't cheat. Kind Camel. Well, that's just delightful, isn't it? Nathalie, there you go. Thank you for participating in our first Kahoot quiz together. That was a lot of fun. Let's head back to our live classes now. So Miss Becker's class is joining us in San Diego. If you guys want to kick us off with a question and come on up, you are good to go. Just unmute that mic.
Hi, nice to see you. Thank you so much. How did 51 Pegasus B get its name, please?
Yes, so very good question. People think, oh, I want to name a planet Zathura or something like that, but our planets tend to be named in a very, very methodical way. So the name of the star around which the planet orbits is 51 Pegasi. So it's in the Pegasus constellation, and it is it's not the 51st brightest star because the brightest star in an entire constellation is called Alpha Pegasi. And then the second brightest star is Beta Pegasi. Then you have to go through the entire Greek alphabet, which is, I think, something like 21 or 22 letters. And then you start counting down numbers. So it's something like the 75th brightest star in the Pegasus constellation. That's the name of the star. When you find an exoplanet, it's sort of like having a guy whose name is John, and then he names his kid John Jr. But then he would name his second kid John Jr. number 2. So when you have an exoplanet, you take the name of the star and you add a lowercase b, because the lowercase a is sort of like the star itself. So the first exoplanet you see is 51 Pegasi b. If there was a second exoplanet, it would be named 51 Pegasi c, and then so on and so forth. But some exoplanets are special enough, they get their own special name, like Osiris, for example. For the most part, we keep with this system, though.
Incidentally, for any student that may grow up and want to be a parent and name all their kids the same name, don't. It's bad. Don't do it.
George Foreman did that.
Georgina, it's the greatest. Anyway, I'm so glad you know that. Westview, let's go to Burlington, Washington. If you guys have a question, in Miss O'Toole's class, come on up and unmute your mic. Welcome in, Westview. Hey guys, I like the lights along the ceiling. Yeah. Photo ball. There we go.
Hey! Anna, our student Angel has a question.
No.
No? Okay.
I will.
Okay, we don't have a question over here. We'll make one up. How long have you worked in your job and what's it like? Do you like it?
Yeah.
Yeah, great question. So I've been sort of in space stuff for about 12 years now. I've always sort of done science communication on top of doing research. I got my PhD in 2016, so 5 years ago now already. I can't believe it. The current job that I hold, I started in 2018, so a little bit over 3 years, and I love it. I cannot believe I get paid to do this. Honestly, I would do this for free. But no, I really love working in space. I've wanted to be an astronomer since I was maybe 5 years old, so I feel really, really privileged to be able to work as an astronomer, and talk about my passion to everyone.
I would do my job for free too, but we're gonna, anyone from James Webb watching, she won't do it for free. Money is important to life. Let's head back in Miss Becker's group, Miss Birch's class. Caitlin and Miss Birch's class was our kind camel, so way to go to her. Miss Birch's group, I know you've had some tech difficulties. If you want to share some questions on YouTube, please do, and any other folks there, come on and share as well. But Miss Becker, back in California, come on back in. Just unmute, you're good. There we go.
There we go. It'll take 4 years before I get it all done. What would happen if you got sucked into a black hole?
Yes, a fan favorite of a question. And luckily, we don't know this firsthand because we have never sent someone to a black hole. We've never even sent a probe to a black hole. The closest black hole is actually hundreds of millions of light years away. So we are in no danger of getting sucked into a black hole. But if you were to fall into a black hole, right now, you might not realize it, but the gravity caused by the Earth that your feet feels is a little bit stronger than what you feel from your head, just because your feet are a little bit closer to the Earth. But because we're a lot smaller than the Earth is, that difference in gravity between our feet and our head is very minor. For a black hole, which has really intense gravity, if you're falling feet first into a black hole, the difference with the gravitational pull that your feet feels is a lot bigger than what your head feels. So you will actually start getting stretched out in a process that is scientifically named spaghettification. You are turned into sort of like a long noodle, and eventually you get sort of like torn to shreds, ripped apart. When all those little bits and pieces of the person fall into the black hole, they sort of get eaten up by the black hole. And the analogy I like to give is if you're eating an apple, a part of that apple will be digested by you, and that will be used to form new cells inside your body. So like we are what we eat. We take what we eat to form more of ourselves. The black hole does the same thing. He gobbles up a person and he takes the atoms and the molecules that make up that person, sort of like sticks it on itself, and the black hole gets a little bit bigger and a little bit heavier when that happens. This is all theoretical, again, because we've never done the experiment, but according to our theories, that's what would happen.
I like how truly excited you are as you're explaining this. It really is the most fun way to die in the universe, I think, spaghettification.
Yeah.
Let's head to YouTube. Miss Birch's class. Welcome in grade 10 through 12. Nice to have a high school group in today. They got a bunch of questions. So the main one, and I feel bad for sharing those, but why was the launch date constantly pushed back? I think when we started doing programs with you like 5 years ago, they're like, it's just about to be here, and here we are. So you tell.
It is a fair question, honestly. And the main reason is because we are sending the James Webb Space Telescope at 1.5 million kilometers away to a place where if it breaks, we cannot fix it. So Hubble, I'm not saying people were careless or anything like that. They were very careful, but when it launched up and it didn't work properly, they had a backup plan. They could send people to fix it. We don't have a second chance for Webb. We don't have a backup plan. So we needed to test it thoroughly. And if we even had an inkling that there might be an issue or a problem during our tests, it was important to iron out that issue while it's on Earth, where humans and astronomers and scientists can deal with the problem, rather than say, it'll probably be fine, and then you launch it up, and then it tries to deploy, and then it sort of like gets stuck, or it doesn't reach its final destination properly. So it's because there is no second chance with Webb, we needed to be really sure and thorough with all of our testing. So it ended up being pushed back as we, encountered these things. But it's really a complex machine. Many argue that this is the most complex machine that's ever been built by humans, and we're strapping it into a rocket and then launching it off into space where it needs to like go on autopilot essentially. So it's very complex. There's no second chance. So we prefer delaying it as needed rather than make a mistake.
I love that answer. It's why rocket science and neuroscience are classically like the things that people say when you're talking about something really complex, is because there's no margin for error. So there's a reason. Thanks, Ms. Birch, for all the questions on YouTube too. This is great. But let's go back to West U. If you guys have one now, come on up and unmute your mic, and you're good to go. No hurry, all good. No rush.
Yes, we do.
What would happen if Jupiter exploded?
We've
So
never gotten that one. That's a first-time question in the history of this program. Thank you for that.
So there's like, if we're imagining that there's no reason for it to explode, it just spontaneously explodes. It depends on the size of the explosion. Jupiter actually is a very important body inside of the solar system. One of the reasons why we think maybe the Earth was able to form and develop life over time without being too bombarded by asteroids that would kill off all the life is because Jupiter is sort of like this big shepherd, and the sheep are like these asteroids. And so the presence of Jupiter actually controls the amount of asteroids that can zoom around in the inner solar system where the Earth is located. So imagining Jupiter were to spontaneously explode, depending on how big the explosion is, it might destroy a bunch of its moons. It might cause a lot of debris that will be blasted off around. But just the very lack of existence of Jupiter may become a problem because all of the sort of asteroids that it's keeping in check will become a lot more erratic and harder to track, and they might end up being launched towards Earth. So we're actually really happy Jupiter exists, and we don't want it to explode.
Good luck for Jupiter. I don't think we run the risk right now, but I like the inspiration. Time flies and you're having fun, folks. So what I want to do is share one more question, or sort of a joint question from Ms. Birch's class, and then we'll highlight some resources where you guys can keep the learning going after you're done. But Ms. Birch's class, they're high schoolers. They want to know, what did you do and learn in school to get into this profession, and what steps did you get what steps did you take to get hired in the role that you're in now?
So I did a lot of science in school. I went to a high school that had like a lot of concentration on science specifically. In Quebec, where I did my education, there's sort of like this in-between step between high school and university called CEGEP. And I went in a program called Science, Letters, and Arts, which allowed you to like do lots of different things, but I focused a lot on physics. After that, I did my bachelor's degree in physics, because really astronomy is just physics that's applied on celestial objects. So there are different pathways to get into astronomy. You can go into engineering, you can go into chemistry, even biology, but really physics is sort of the classical way to do it. I then did a master's and a PhD in astronomy and astrophysics. One skill that's pretty important in almost all sciences, but especially astronomy, is programming. We use a lot of computer programs that we sometimes write ourselves to analyze our data and try to figure out scientific results. So programming is very important. With the job that I have now, a lot of what I do, however, is communication. So I've been doing science communication. At the start, it was more volunteer work. And then afterwards, I was in charge of the campus observatory when I was doing my master's, my PhD. And then I had another job after my PhD, which like focused a lot on education and science communication. So I just started doing sort of volunteer work, and then I gained more and more experience with different audiences and different formats and content. So I have like a really nice mix of a science and communication background now, which allowed me to get this role.
That was a very detailed answer. I love that. Nathalie, one thing that I want to highlight for our high school classes, and it's often a little daunting. If you're in grade 10, you're 16, you're 18, sorry, frog in my throat. The idea of 10 years of school after you're done high school can be daunting and scary and terrifying, and it's not for everybody. A lot of the colleagues that I had in high school did not go on to go to university, or they did just a bachelor's degree. But if you are keen on this as a path, it sounds a little crazy, but you end up really young in a career where you get to work with people all over the world. You get to travel, you get to, fulfill your passions every single day, which is a pretty exciting thing. So again, I hope some of the students in those classes, if you are keen on this and going the PhD route, there's a lot of perks and benefits in following in that path. Nathalie, we could talk all day. I know you've got a graduate student talk after this. I hope ours is a little bit more fun than those older students. But I want to make sure that our folks have ways of finding out more about the work that you do. I know you're very active on social media. If people want to check you out on Angry Astro Panda, which is our most fun social media handle we share all week, or learn more about the James Webb Space Telescope at jwst.nasa.gov. Shockingly great education resources for a government website. So check out NASA's stuff. It's some awesome content, and I hope you guys are all inspired to learn more. Nathalie, is there any last message you want to share before we wrap up and bring in our classes to say a big farewell?
So December 18th, stay tuned. This is the launch date. It might move a little bit, but we're really, really close to the launch. It's being prepped right now in Kourou in South America. And next year's going to be a huge year. Lots of new discoveries and results. So stay tuned. Keep your eyes peeled, your ears peeled. And I hope I got you excited for James Webb.
I'm so excited to have you back after it's launched. I cannot wait to highlight what's going on with it once it's out there. And as you know, we wrap up every broadcast by saying a big thank you and farewell. So Miss Becker and Westview class, unmute your mics. Join me. Thank you guys so much. And have a wonderful rest of your day. Bye, everybody.